It's amazing what nerds will do to rickroll each other. It
I
creates the real fun in the world.
I have actually the entire B2B script in hexadecimal to be able to send over a packet data. So that way,
That is
if
some-
everyone ever decodes it into ASCII, they instantly have the entire movie script.
So this is an interesting day for lack of attendance, I guess. We have a couple of people remote, but there are almost 30 people in here, and we have what, maybe 15 total?
There, she's
So, yeah, as I mentioned, today's going to be a pretty important lecture because we're going over a very important algorithm that will be relevant to we'll be implementing it for your first programming project. So we want to take the time to make sure this is as intuitive as it can be. And it's really not that bad. It just, once it clicks, and it's not too bad. But getting to that point can take a little bit, just as most stuff in this course does. So we should take the time to make sure that we get there. So we mentioned Chomsky normal form. We talked about the two possible production types, Chomsky normal form. We either have a non-terminal to exactly two non-terminals, or a non-terminal to a single terminal. Those are the only two production types allowed, and we can guarantee that given any non-lambda context-free grammar, there is an equivalent CNF grammar. So we're going to start calling Chomsky normal form just CNF because we say it a lot. And we have an aversion to saying people's ones giving me credit. So let's talk about how we convert into CNF. It's the most important thing to do if you have a grammar that you want to answer the membership problem to, and it's not in CNF. So as input, we need to take a grammar. It cannot have any lambda productions anywhere in a right-hand side. If it does, then we need to find an equivalent grammar that does not. But we also know that for any grammar, we can remove the lambdas from the grammar. So we're going to parse the input grammar and construct an equivalent grammar. We are going to start by looking at just any productions of particular forms. So we expect to see non-terminal arrow, some list of terminals and or non-terminals. That's every context-free grammar has that particular form. So we're going to start by breaking down the right-hand side into its components, terminals and non-terminals. Think of it like an array. This is how you would store it. If we query the size and it is 1, we know that it has to be a terminal. Then we're going to introduce new non-terminals for every terminal in each production. We're going to be going through and saying we're going to take the first character out and everything else is going to get crunched into another new non-terminal. This is way easier than it sounds when I describe the steps. I'm starting to think that I should start with an example and then describe the steps, because otherwise I just feel like I'm going through this. It would be better to just jump to the example so that you can see what that looks like. Let's see if I can just do that. So basically what we're doing is we're looking for places where we can just make the second production type in CNF, where we can just say, all right, we can now have non-terminal arrow terminal. Great, done. If there's more than that embedded in this, then we need non-terminals to cover basically everything that would be left. There are no terminals in any production of length greater than 1 by the time you go through this step. So for each of the non-terminals introduced here, we'll add a production that just converts them into their terminal expressions. So we're first introducing non-terminals for every terminal. We're just going through looking for any terminal and saying there is a non-terminal that maps directly to this. So if somewhere in a grammar we were to see something like S arrow A capital S B, this is not a legal CNF grammar. No, it also doesn't terminate, but you could assume that maybe we have or A. doesn't matter. For every terminal, we're just gonna create a non-terminal that maps directly to it. So we could do something like, say, introduce this is in CNF. And now we can do a replacement of every place we see that terminal with a non-terminal in the rest of the grammar. And what's left is just sequences of non-terminals. By the time we do this, what we need to parse that's not in CNF is now lists of non-terminals. So this entire part 2 is just about parsing through those lists of non-terminals, because every terminal had a non-terminal made for it that maps directly to it.
Would this still not be in CNF?
Not yet.
The starting one?
Yeah,
How would you break?
this one is where we're gonna introduce part 2. Basically, we've now produced through step 1, the larger step 1, and now we're ready to do this part on that. So yeah, this is just the first half, and now we have to handle this monstrosity. So the idea is, since we can only have non-terminal arrow exactly 2 non-terminals, we're going to be doing the equivalence of composition, object composition. So we're going to be saying something like, well, we need to be able to group these together in some new non-terminal. So we could do something that says something like C arrow SB. And now we replace this SB with a C. And now it is in CNF. Because we have now introduced this new higher level of abstraction non-terminal that represents 2 non-terminals that would come together. So all this is saying is every production is a list of non-terminals. So how we're going to do this is we're going to break out everything after the first one and make an object that represents that sequence. Then recurse on that, because that may be length greater than 2. So maybe we have some production that looks something like A, B, C, D, E. And we want to break this apart. We do object composition of B, C, D, E, and we're going to call that something like F. So F is going to be the equivalent of B, C, D, E. But it lets us replace this entire concept with F. So now we have one right-hand side in CNF. And now we just have to recurse and break this apart, but the size of this is 1 less than the size that was. So we can do object composition of this, breaking this into a G arrow C, D, E, replace all of this with just G, and recurse. So we're just breaking off the first one and everything else into some new non-terminal, recursing doing that until we only have exactly 2 non-terminals left in the largest list of non-terminals. So we would have something like AF, BG, and then we do this one more time to say something like H arrow DE and replace. And now everything looks like it's in CNF. So this is why for any context-free grammar, there is an equivalent in CNF, is we just follow these rules. And this is just saying a little bit more mathematically that intuitive concept. 1 and 2.
There a world where you run out of capital letters?
Yes.
So given that, would I index them like how you have this?
You can do something like subscripts, those work. You can start to use Greek letters, you can start to use other symbols, it's up to you. You could even use more than 1 character to represent a single non-terminal. You could have a non-terminal that was AA defined to be something, but that starts to get really hard to read.
Right.
Especially if there's the ambiguity of if there's an A and an AA, you see an AA on the right-hand side, what does that map to? So you would have to make sure that there is no partial overlap between any of those. But yes, you can absolutely run out of capital letters.
When you reach the list of non-terminals of size 4, could you just put that into 2 separate ones? Instead of doing group 1 and 3 and then a group of.
Yeah, if you do 2 and 2 for that, then you end up having to it does work. So you're saying something like we have A, B, C, D, yeah, use a kind of a more of a binary search. If we had this, we could say S arrow 2 new values here that was E and F, where E represents AB and F represents CD.
But that works though.
Yeah, that would work. Questions about that? My eraser go, it's all the way on the other, there's one there, there's one here. I'll grab this. Yeah, they always do that. I leave them right here and then someone else comes in here and says, you know, it would be better than using this on the board, playing basketball. Dodge eraser. The new sport that keeps us in shape. You do it in the classroom. All right, so that's breaking this down into CNF. So it's really not too bad. So doing something like converting this grammar into CNF. Let's see if we can quickly knock this out. So remember that step 1 was introducing new non-terminals representing the terminals. So we just need the ability to do that. Yeah. You can name these whatever you want. You can either have A sub 1, you can rename the other non-terminals to be something else, whatever makes the most sense to you. I'll just use C, D, and E. So now we can replace what's here. This is capital A, capital D, capital C. This is capital C, capital C, capital D. And this is capital A, and then capital D. So this is already in CNF. So we don't need to do anything to it. But we need to break apart these first two. So we need some way now to represent DC. So we're going to introduce a new non-terminal that is DC. And we can replace this DC with an F. We need something that represents CD. So we're going to have a non-terminal. And even though these are flipped, doesn't matter. They're different, they're distinct. So we'll replace this CD with AG. And now we have everything in CNF.
Why did we replace the C? Why did we create a G for CD? Is it because it already exists or something?
It's because we can't have 3 non-terminals in a row. So we needed to apply the rule where we keep the first one, everything else gets bunched together into some new non-terminal.
Is there any like way to like check you got it in these like numerically? Like if I have this grammar, I know there's gonna be this many productions to get it in.
Yes, because we need every pair that's already there. So you could analyze based on the length after step 1. So you would know how many terminals you have based on the language. And then you would know how many non-terminals you're going to have by when you look at the length of each one of these. Anything that's length 3 has to be broken down into 2. Anything that's length 2 is already going to be good. You may be able to reuse some of these if you intelligently see that the first 2 map to something that exists. So you can make these a little bit smaller. But if you're algorithmically making this process or doing this process, then you just need some way to ensure that it works. Questions on the process? Does that make sense? Certainly not the most difficult thing we've done in here at 10 pumping load. So that's what that process looks like. And we get something that looks like this. And again, exactly how you state this, doesn't really matter. Here we can see that we're using some sequence of subscripts to say that this now maps to that particular character. That's frequently a very clean and clear way to show that, but I wanted to show it named slightly differently in case, for some reason, one of these makes more sense than the other. I don't care, the grader doesn't care, as long as it's clear and consistent and mathematically sound. So we end up with something like that. I will briefly introduce the concept of Greibach normal form before we come back to it in a unit or two to talk about it in a little bit more detail. But just to give you the definition of what the forms are for it, any non-terminal is going to be a single terminal followed by 0 or more non-terminals. So it's kind of the exact reverse of the regular grammar, where if it was left linear, you'd have a single non-terminal followed by 0 or more terminals. Just flip what terminal and non-terminal is from left linear and you get Greibach normal form. We will see when this will be a very important form to have for grammar in a bit. So I don't think it's important, super important for us to go through this at the moment, but we'll come back and again explore it in a bit more detail. Not gonna see it in quite as much depth. All right, two big normal forms. CNF is the really important one because it will help us with the membership question. So we're gonna dive into the membership algorithm, and I think I have enough time to actually do this some justice. We'll probably still come back tomorrow and finish it off, but we've asked this question and we've determined that the brute force method of this is disgusting. Is the query string in the language defined by the grammar? We have a string and we need to answer yes or no, this string is in the language defined by this grammar, or no, this string is not. It turns out if we have a grammar that's in CNF, we don't have to use brute force. And there exists a much cleaner and nicer way to do this, at least in terms of complexity. So we're going to introduce a cubic time algorithm to solve this problem in general, which is nice and polynomial and doesn't hate us like brute force does. So we need to define a few things going in. The characters in the string that we're using is going to be subscript lowercase c's, C1, C2, C3, up to C capital L, where capital L is the length of that string. We're going to say, we're going to define a substring as W sub ij, which just says this is the substring from character I up to and including character J. So unlike how Java's substring works, for instance, which goes up to but not including that last character, we are going to say Wij is up to and including that last character.
And I is also.
Yes, yeah. It's inclusive on both ends. Now we're going to define capital Nij as a subset of non-terminals that could produce that substring. Basically, if we're starting at a particular non-terminal, can we produce that substring using that non-terminal as the start non-terminal? So we know for grammars, we've been saying that capital S is always the start non-terminal. We will be answering this capital Nij as the set of non-terminals that could produce a substring via some sequence of applications of the productions. We'll see what that means here in a second. The final answer is going to be if we can determine that the start non-terminal is in n sub 1 lowercase n, which is going to be the length of the string. It's capital L up here, but this is just the length of the string. So if the start non-terminal can produce the entire string, then we're good. That answers that question, right? But we need to build this up using dynamic programming to save us the time of having to re-answer these queries over and over and over and over again. So we're going to be intelligently storing information for later lookup so that we reduce an exponential complexity algorithm down into something that is polynomial. So how familiar are we with dynamic programming? Maybe a show of thumbs, really comfortable with it, we know what it is. I can tell you the definition, but don't have a ton of experience with it. Say what again? All right, lots of mid to low thumbs and a couple of thumbs up. So we're going to be doing this kind of introduction of dynamic programming to talk about how this is one of the most important algorithmic techniques that you can know going into industry. So it's very important for you to study this, know it, and be able to perform it in interviews. For those of you going off and doing interviews in the world, because they frequently test your knowledge of dynamic programming as a way to distinguish those who are prepared and those who are not. Yeah.
Just to confirm, dynamic programming is basically just caching data, right?
Yeah.
Yeah.
Yeah, you're using a lookup table and building a lookup table based on partially completed solutions, and then answering questions for larger solutions based on the optimal solutions to the smaller problems that make up that larger problem. So you're recursively defining the problem in terms of a sequence of smaller problems, smaller, 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 smaller. And then instead of asking the big question first, you ask all the small questions and build up the slightly bigger, slightly bigger, slightly bigger until you can answer the initial question.
Isn't that just a divide and conquer algorithm?
It can be. But divide and conquer can also just be recursive. And this is recursive with storing information so that the bigger questions are just lookups by the time you get to them. So something like merge sort, for instance, didn't involve any lookup table. It's still divide and conquer, but you can just recursively define the solution to merge sort. We could recursively define the solution to this, but it would be exponential complexity to start at the high end. We would find ourselves solving the small subproblems over and over and over and over an exponential number of times. So if we just store that, so when we can recognize we're asking a question that we already answered sometime in the past, then it becomes a lookup instead of a recalc. That's really all there is to dynamic programming. It's not crazy complicated if you can break it down and understand it recursively and what you need to store to get that bigger solution. So let's do it. How we're going to do this is we need to start with this question of, can we produce the single characters? So this says, for which set of productions can we produce a particular character within the string? Because this sub I tells you that the substring length is 1 from position 0 to position 0. That is the first character in the string. What set of productions in the grammar, if we started there, could generate just that string and call it in the language? Could we terminate the grammar at that point? Again, we'll get an example of this. And then we need to answer all of for every possible substring. At this point, we can now break it down into a possible midpoint and then analyze based on that midpoint. The midpoint is going to involve lookups to smaller substrings. So we're going to build up larger and larger substrings, being able to say, if we have something like a 5-character solution, and we want to know which productions can produce this exact sequence, we can now break it up based on a possible midpoint and say, here's a left side, here's a right side, here's a left side, here's a right side, here's a left side, here's a right side, here's a left side, here's a right side. So if we can break this down into some such midpoint, such that we can, based on the answers to whether substring can produce this left side and this right side, if they can produce this, and we have a non-terminal in the form that can produce the left side and the right side, which are these two non-terminals in CNF, you'd have a non-terminal representing the left side and a non-terminal representing the right side for some left side, right side breakdown. Then you could say that the non-terminal, that would be something like S arrow, that left side, that right side, this is now in the set for defining this. Again, this needs an example. I trying to prime people as much as possible, breaking this down into a left side and a right side for something that's more complex. That's all this is saying. So if there's some production, non-terminal arrow, two non-terminals that can produce a left side and a right side for some midpoint K between I and J, then we can add that production into a set that can produce this substring. We answer that for every possible breakdown, and then we move on to the next, and we just start going longer and longer possible substrings until we have an answer for the whole problem. So we proceed. Step one is computing all capital N II, so all single character substrings. So this will look at the first character, the second character, up to the length of the strings character. After you have all of that, when you have, we're going to look at substrings of length 2. So we're going to look at the first two characters, then the second and third character, up until the length of the string -1 and the length of the string character. And there's only one possible midpoint for a string of size 2 right in the middle. The left and the right are going to be strings of size 1, which we already computed. So it's just a lookup into what we've already computed to be able to fill in this second one. Once we do that, we're going to look at all substrings of length 3. But now there are two possible midpoints. Either the left side is size 1 and the right side is size 2, or the left side is size 2 and the right side is size 1. So we're going to look at both of those to come up with the answer for each one of these cells. And we're going to fill in, just like before, a triangular table until we have a cell that represents the entire string. We continue this process until we terminate when we're looking at the entire string. Is the start non-terminal in that set? If it is, then the grammar can generate that string. If it is not, the grammar cannot generate that string. Conceptual large questions before we start an example of this and fully draw this out on the board step by step? Yeah.
So to my understanding, normally in dynamic programs like this, we're trying to find the best optimal answer to move forward with.
Yeah, this is just a yes, no. It's not even an optimization. We're answering a yes, no question by asking the question, is one symbol in a set for the entire string? To even be able to answer that question, we have to break that down into all substrings of length 4, 3, 2, and 1 to be able to answer that. If you have a string of length 5, if you break that as a possible midpoint down into 1 character followed by 4 characters, then you need a lookup in the row of a single character substring and a lookup in a size 4. So to be able to even answer that, we have to break down and have lookups for every possible cell in the table already, which is why we need to have done that and stored that in advance, because we're going to be asking those kinds of questions over and over and over again. Better to ask it once and answer it once than ask it a bunch of times. That's the difference between a polynomial time algorithm and an exponential time algorithm. It's just how many times do you ask each sub-question? If you ask a question you've already answered, it's silly. Let's dive into it. If there aren't any more questions, I'll give you the grammar that we're going to use. This is a grammar in CNF. So we need to start by coming up with the string. We see the string is AABBB. So the question we are trying to answer is, can this grammar generate this string, starting at the start non-terminal? Can we generate AABBB via some sequence of production applications? And this process will scale to arbitrarily large grammars. We're using a smaller example here just to illustrate the point, but you can imagine if you were trying to answer a large scale question like, is this program in Java? Then it becomes much longer, a much bigger grammar, a much harder process that we actually need a computer for. But it's very much exactly what this is doing. So let's set up the table first and foremost. Actually, I don't even know if I want to go into the rest. I just want to draw it out. So we are going to, how do we want to do this? Sure, this is big enough. One, two, three, four, five. So this cell is where our answer is going to be. This represents 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. This represents 1, 2, 2, 3, 3, 4, and 4, 5. 1, 3, 2, 4, 3, 5. 1, 4, 2, 5, and 1, 5. So these are the subscript bounds on the string. So this is looking at character starting at 1, ending at 1, starting at 2, ending at 2. So this represents just this first A. This represents this second A. This represents this first B. This represents AA. This represents AB. So just all of the possible substring bounds. This is going to become the table that we fill in, and we need to fill in row by row, starting at the bottom. We're going to fill in each of these, and then to fill in these, they're going to be lookups to here. To fill in these, they're going to be lookups to everything you've done so far. To fill in these, they're going to be lookups to everything you've done so far, until we can fill in that top left box. So it looks kind of like a triangular table. This is how I like to visualize it. So let's actually go through the process of starting with 1, 1. Basically, this says, here is our substring, it's just this A. Are there any productions here that can immediately just produce A and terminate? A arrow lowercase a. So what goes in each of these is going to be a set of non-terminals. So the answer to 1, 1 is just A. And that if we were at A and needed to produce a single A, we could do so.
It wouldn't be this, it wouldn't be in this language.
Correct. Not immediately, because we can't do it from the start non-terminal. But this may become the left-hand side or the right-hand side when we're looking at something like AA. This is going to break down into, can we generate a left-hand side and a right-hand side, each of which can produce that non-terminal. So we're not answering, can the language generate lowercase a? We're saying if we were to break this into a left-hand side and a right-hand side, and the left-hand side were A, then maybe we could produce some combination of that in a way that now the start non-terminal can produce something. So it's important to think of, this is not, we're not asking anything about the start non-terminal until we're all the way at the end. How are we doing? Does that make sense? Questions about that? All right, 2, 2, what's the answer? A, it's the same thing. We're looking now at this substring. How about 3, 3?
B.
Just B. How about 4, 4? Just B. Enjoy the easy step while we have it. So we filled out the first row, which is great. This is always going to be the easy part, because we can see direct mappings to, can a single non-terminal produce the exact terminal that is that character at that position in the string. For 1, 2 now, any questions about filling this out before we move on to the next row? All right, 1, 2 is this AA. I'm kind of gonna bring this down for a moment and say, can we produce a left-hand side and a right-hand side? Okay, there's only one way to do this at the moment, which is very nice. But we need a left-hand side that produces an A and a right-hand side that produces an A. How can we answer this problem?
1, 1, and 2, 2. can reduce.
Yeah, so we can come up and say, well, either this or this could be the left-hand side. So we need something that is capital A or capital A. So the only way to produce this is via capital A. The only way to produce this is via capital A. So the right-hand side of a non-terminal that we are looking for is AA. Does AA appear as the right-hand side of any production in the grammar? No. The answer to this cell is the empty set. Nothing can generate a left-hand side and a right-hand side such that at that non-terminal, we could break it down to be able to produce this substring AA. Cannot be done. Question?
How do you know it was the right hand side? Or is that just what you're only?
So we're breaking this AA down. There's only one possible midpoint right in the middle. There needs to be a left-hand side of at least one character and a right-hand side of at least one character. So there's only one way to break that down. The left-hand side needs to be able to produce a single A. The right-hand side to produce a single A. And we can look this up in our table, actually, if we see that this A here is this subset, and this right A is this subset. So we're looking at this cell, and then this cell to combine. This cell is the left-hand side, this cell is the right-hand side. Concatenate every possibility. You're creating tuples from everything from this set and everything from that set, which is what we did on the very first day of class, coming up with and defining tuples as elements of sets to come up with the cross product. So that's all we're doing here is we're querying the cross product of elements of this set and then looking for each one of those as the right-hand side in the grammar.
So but you're only checking the right hand sides of the grammar?
Yes, we're looking for pairs of non-terminals that map to the pairs of non-terminals that we will see from coming up with the cross product of these two sets.
You need a production that maps directly to A.
Yep,
In that table or some set of productions we've extrapolated from.
yep. And none exist. So I think we're ready for the next one. Instead of a question on index 1 to 2, we're going to ask index 2 to 3. This produces this AB. So this is a lookup to a left-hand side. This is 2, 2, and this is 3, 3. So we're going to pull from 2, 2 as the left-hand side. That's an A. We're going to pull from 3, 3. That's a B. We're going to combine these and look for any ABs in the right-hand side of a production. S and B. So this set contains both S and B as the way to produce the AB that is the lookup for what we've already stored. Does that make sense? How do we do 3, 4?
Okay,
We're going to now look at this BB. We break it apart into this is 3, 3, and this is 4, 4. So we're going to look into our table and we see B and B. So we're going to bring down the set that is a B and the set that is a B. We are now looking for BB showing up somewhere on the right-hand side, and we see that, sure enough, one of our non-terminals can produce it. So we're going to add that non-terminal to the set that goes at this point in the table. Because A is the left-hand side of a production that produces BB, which is what we try to find right here. That's the logic to get there. What's nice is we just did this work, didn't we? We know that for the last one, 4, 4, 5, 5, BB, we just did that work. So this answer will also be just A. All right, we ready to level up the difficulty? All right, here's where you actually want to start keeping track of what you are doing, because here comes the cubic part of it. So far, it's just been quadratic and it's been nice. 1-3 says we're gonna look at the first three characters, A, A, B. Now there are options for how to break this apart. We can have two possible left-hand sides and two possible right-hand sides. So I'm going to break this now into that and that. So we're going to start with the left-hand side, right-hand side. The left-hand side of this is just 1, 1. The right-hand side, AB, is 2 to 3. The other possibility is a left-hand side that is AA, so 1, 2. And a right-hand side of 3, 3. Those are our two options to concatenate a left-hand side and a right-hand side together to make the substring 1, 3. So a lookup to 1, 1 says this is A. A lookup to 2, 3 says S and B. Since we're taking the cross product of this, we want to take an element of this set and an element of this set. This gives us both AS and AB. One, 2 is the empty set. 3, 3 is just B. The cross product of this is nothing. So what goes in this block are all such AS or AB productions in the right-hand side. And we see that both S and B can produce AB. So what goes here is S and B. What questions do we have on that?
You just put in S and B right there, you put it in A.
You put it just right here. Just S and B.
Why don't you add in the A?
Because that would require BB to be somewhere. And the only options we have are AS and AB. So we want all left-hand sides of productions that can produce either an AS or an AB. And A cannot produce either one of those. S can produce AB, B can produce AB. So from this AB, we get S and B.
You need to find the productions that produce the cross product.
Yeah, so you're gonna take the cross product, and then you're gonna take the union of all non-terminals that can produce any one of those or more. So to fill out 2, 4. Does that make sense? Any other questions on this? How are we doing? Make sense so far?
Are you only ever gonna recurse down to the layer below it, like with any reasonable split?
Anywhere in here. We saw for this, we had to do a lookup of length 1 and length 2. So it referred to something in the first row and something in the second row. So yeah, we do need everything else in the table, not just the row below it. Let's do the next one. Next one's going to be that substring. So we can either break that down into AB followed by B, or A followed by BB, which is the equivalent of, this is 2, 3, this is 4, 4, this is 2, 2, and this is 3, 4. Looking down into our table, 2, 3 is the set SB. 4, 4 is just B. Taking the cross product, this gives us SB or BB. 2, 2 was A. 3, 4 was A. Cross product just gives us AA. So now we have 3 things to look for any productions on the right-hand side that can produce SB, BB, or AA. And it's just A that produces this BB. Nothing produces an SB, nothing produces an AA, but the A is what produces this BB. So it's the A that goes in this spot. As the left-hand side that can produce one of these left-hand side, right-hand side pairs for analyzing the cross product of the sets generated from the possible midpoints from this string. Let's go. We doing okay? Next one. BBB can be broken down into 3, 3, and 4, 5, or 3, 4, and 5, 5. So 3, 3 gives us B, 4, 5 gives us A, combined gives us BA, it's the only option for that cross product. 3, 4 gives us A, 5, 5 gives us B, so we're looking for AB. So again, taking the union of what can produce BA and what can produce AB, what do we get?
S, B.
S and B. It's the only non-terminals, the left-hand side that can produce that. We're gonna level up the difficulty again because we're going up a row. More possible midpoints. So now to answer the question for AABB, we can have a left-hand side that is 1, 1 and a right-hand side that is 2, 4. We can have a left-hand side that is 1, 2 and a right-hand side that is 3, 4, or a left-hand side that is 1, 3 and a right-hand side that is 4, 4. So now we have 3 different branches. Do we need to take the union of? So left-hand side, 1, 1 is A. 2, 4, we already calculated, is A, giving us just AA from this side. 1, 2 was empty. And we can now just start to shortcut. If any of these are empty, the cross product is going to be empty. No reason to even do that lookup. Empty. 1, 3 was, I'm going to draw it as a set, S and B. And 4, 4 was just B. So that would give us SB and BB. What is the union of all left-hand sides that could produce any of these right-hand sides? BB. Just A, producing this BB. Nothing produces an AA, nothing produces an SB. Just the A produces the BB, so that's what goes here. Two more. We have just enough time, I think. We'll do it. 3 possibilities for the midpoint. We can have 2, 2, followed by 3, 5. We could have 2, 3, followed by 4, 5. And we could have 2, 4, followed by 5, 5. So let's again break this down and look at 2, 2 is A. 3, 5 is S and B. We have A and SB. These should technically all be drawn with sets, but if it's just size 1, I'm just writing it. Cross product gives us AS and AB. 2, 3 is S and B. 4, 5 is just A, giving us SA and BA as the possibilities. 2, 4 is just an A, and 5, 5 is just a B. So this gives us AB. 5 possibilities now. What left-hand sides can produce any of these? Just S and B. So that's what we put in that box. Last question, just as time expires. Now we need to break up every possible middle point in this But since we have a complete table, we have answers to every possible substring of this. So this is a really easy lookup now that we've done all of the rest of this. So how could we break this down? There are gonna be 4 of these. We're gonna have 1, 1, followed by 2, 5. We could have 1, 2, followed by 3, 5. We could have 1, 3, followed by 4, 5. Or we could have 1, 4, followed by 5, 5. So 1, 1 is A. 2, 5 is SB. 1, 2 is empty, so we're not going to consider anything. This is AS and AB. This will just become the empty set. 1, 3 is S and B. 4, 5 is just A, giving us SA and BA. 1, 4 is A. 5, 5 is B, giving us just AB. What's the union of left-hand sides?
S and B.
S and B. That's what goes in this cell. So the question that we wanted to answer from the very beginning is just, is S in this set? Since the answer is yes, this string can be produced by this grammar. If S did not appear in this set, then that string could not be produced by that grammar.
Only in that final one.
Yep. In this cell is S present in that set. But to answer this, you see that we had to look up all through this table in a way that recursively, if you recursively define each one of these, would use every single one of these cells. So you cannot skip any of this work. The size of this table will grow based on the size of the query string.
And the number of productions.
And the number of productions is how much you're going to be, yeah. So you can see that this is cubic because we already have length of string, some breakdown, the maximum number of substrings that you have to query is the length of the string minus 1. So we get 3 dimensions based on the length of the string. This ends up being a cubic time algorithm.
As soon as you see the AB in that first one and you know that S can generate AB, would you stop and enforce them for this final one?
Yeah, as soon as you have a way that S could be generated, you could terminate the whole thing.
Wait, so wouldn't you be able to stop at?
At where? Here?
Yeah.
Not necessarily, because you still need something from the 4, 5. I guess you could say here from the 4, 5 we've already done, that you can produce something, the S, the A and the B. No, it's,
I was meaning that in the first one, usually 1, 1, and 2, 5, you find the AS.
oh, yeah, since you had the AB here. Yeah, all the rest of this was unnecessary. Once you generated something that could generate the S. But yeah, you can't stop anywhere filling in this table before you get to that point.
We're gonna,
If anyone needs to run off to another class, you're welcome to pack up and head out, but I'll answer any other questions we have before, just so we don't cut this off abruptly.
I'm assuming this is probably like encroaching on the coding project, but what kind of structure would you use to store all this information? Like a hash table?
So this is just a 2D array. I would store this as a 2D array of set objects. And then you're going to be filling in each one of these by querying all of these breakdowns. There is an algorithmic process for figuring out what all those substrings are. And you, given a substring, think of all for each possible midpoint. Look up in those tables, what are the indices of those substrings? So if you can come up with that lookup algorithm, then you can automatically fill in the value of a single cell, assuming that everything below it in that table has been filled in.
Right, you would just be like, check, like, is this cell empty? And then if it's not, then you have to recalculate it, or you can just look at it.
Yeah, you can always look at it. There was never any time that we had to redo a calculation. Anything that we redid was a lookup in the table. And note that if you were doing this via brute force, every time we did a lookup, you would have to be resolving that problem. How many times did we look up something in this first row? A lot. How many times did we look up something in the second row? A lot. Each one of those we'd have to redo for every time that we did something, which is what turns it from a polynomial time algorithm to an exponential time algorithm. It doesn't seem that much worse for a toy problem, but remember that we add a sixth character, it adds 1, 2, 3, 4, 5, 6 new cells to look at. So this is growing with proportion to the square, the size of that. And then as we get higher and higher in this table, there are more possible midpoint breakdowns.
Mention this is the CY for the other.
Yes, yeah, this is known as CYK. And implementing CYK will be your first programming project.
You said you would store this as 2-year or 1 year?
2D. It's kind of a jagged array, which would be great if Java supported, but it doesn't.
Write your own.
Sorry?
You could write your own.
Yeah, write your own language, write a compiler, and then solve the
I just meant writing a jagged.
solve the parsing part of the compiler that you need to implement it to do it in the first place by recursively define making a
In
language
order
in
to
terms of
beat the
making a language.
boss, use the boss's key bit after beating the boss.
Yes. Exactly. Last minute questions? We're very over time. People need to pack up and leave, but I'll leave this up in case there are any lingering questions that people have on this.
Here's 2 programming. What is the second one?
The second one is LL.
Oh,
I wanna go to the flat hours also.
Well, at least it's an LL1 lookup. It's an LL.
so does that stand?
Yeah. It stands for,
You didn't get it.
I don't know off the top of my head, I will beat myself over the head when I look it up and it's duh. Yeah, I'll get you that here, Mo.